this mean? Well, if you have a function 2x, you play the game. Who's coming on Friday? To figure out a function whose derivative is 2x, well, it could be x squared, it could be x squared equals 3. They would both work. There are a ton of them, which all differ by a constant, which we would write as the original function had to have been x squared plus c. Again, and this is what chapter 5 is all about. It's finding the original function. So there is a bunch of them. There's actually infinite solutions. The whole family of functions whose derivative is 2x is x squared plus c. But if I said this, if I said I know the derivative of some function is equal to 2x, and I know a point on the original function, f of 0 is 5. With that information, you can lock in the exact original function. Yeah, so I know that f of x had to have been x squared plus that constant. And now check this out. I have an x and a y value on the original function. So with the x and the y value, you can then solve for the c. Just by plugging it in. 5 equals 0 squared plus c. So c has to have then equaled 5. So by taking the antiderivative, you can get the whole family, Marco, all of them. And then if you give me one point on the original equation, you've just locked in the exact function. Okay? So now here's where it gets really fun. Who's my physics people in here? Where are you at? I see ya. Where are you at? All right. And anyone who's taken physics ever at Jones, where are you at? Never? Never at Jones? What is this? Let's try it again. Who's ever taken physics at Jones here? Let me see some hands. Did you take it? Oh yeah, we're taking it. All right, good. So you guys will like this. What's good about calculus is you have to memorize a lot less equations because you can just create them. For example, remember all those like position, velocity, all of that stuff? You know what I'm saying? Well, that's for the birds, I tell you. Who? The birds. Here's why. I take the derivative of position and I get what? Velocity. I take the derivative of velocity, I get what? Oh, here's fun. Where are you at? Everyone's shy around velocity, but we got that acceleration. I like it. Okay. All right, well, on Earth, in meters per second squared, the acceleration is equal to 9.81 meters per second squared, or 32.2 feet per second squared. Okay? That's on Earth. If I knew this, yes, just a constant that people have measured before, so I'm not lying. What would the velocity equation be then for any time? Or in this case, not x, but t plus some constant, right? Or if I took the derivative of this, I'll get that. Now, what is c, though? Well, check this out. If I said t equal to 0, then v of 0 would equal 0 plus c. So v of, this v of 0 would equal c. Well, what is that?
Your initial velocity.
Initial velocity. Is your velocity at time 0. And we write that like this. Do we recognize this equation at all? Okay. Position would be the antiderivative of this. Well, this one's a little trickier. How can I figure out, because that means this had to have been a what in order to get a t here, if I take the derivative? Yeah, it had been a t squared. So what do I have to do to this number in order to... Yeah, you have to half it. Does that make sense? You have to half this number so that when I take the derivative, the 2's would kind of cancel out. Either you can write it as 4 point, whatever it is.
4.9.
Thanks. Or whatever, or I just wrote it in front like that, okay? But somewhere that you gotta half it, okay? So 1/2 times this. Okay, what about this one?
V naught t.
Yeah, plus v naught times time. So if I take the derivative of all of this, I'll get that, right? And then I just have some constant. Well, what is that constant? Yeah, well the constant would be, okay, when time is 0, this would be 0, this would be 0, s of 0 would equal that constant. Well, what does that stand for? Well, that means that's your initial position. That's s naught. Does that make sense? And if you just put in, like, in general, like, instead of 9.8, if I just put a, because that's what the acceleration was, and just a, here's your equations that you guys have been memorizing. Memorizing, that's for the birds. You just derive them. Isn't that more fun? You don't have to memorize it. You can just, oh, what's the position? Okay, well, let's see. Acceleration on Earth is 9.8, so the integral of that, or the antiderivative of that would be a times t plus a constant. So the constant would be, let's see, the constant would be the initial velocity, I guess. Okay. Then if I take the antiderivative of that, I would have the half of that with the square now, and then you would have a t with the v naught, and then of course a constant, because when you need some constant there, and then that constant, that would have to be when everything is 0, so that would be the initial position. So there's my equation. Why waste your brains? You know what I'm saying? You can just derive it. Isn't that fun? Isn't it? That was my impersonation of you guys again. You know what I'm saying? Like, Ms. Kovacs, I believe if you just, yes, I don't need to memorize it. Okay? So things to keep in mind. We're also going to do some fun stuff like second semester where you're actually going to create the equation of volume of a sphere and things like that. You guys are actually going to create it with using calculus, which is kind of neat. You know what I'm saying? So you don't have to memorize. You can be like, what's the sphere? Okay, hold on a second. You're going to be like, okay, so volume of a sphere, let's see, and you're going to do these little symbols, and you're just going to create it, which is kind of fun. You know what I'm saying? Isn't it? No? Okay. We got like a couple minutes up. Start on the homework. 4.2, 3 to 33, multiples of 3.